For our last problem, let's consider a firm that manufactures integrated circuits, or chips. Based on extensive testing of a sample of 1,000 chips, the firm finds that the defect rate is 10%. So 10% of chips are defective. The firm then examines its inspectors' abilities to differentiate between defective and non-defective chips, finding that the inspectors typically had a 5% error rate on both defective and non-defective chips. The company's main objective is to reduce the probability of shipping defective chips. Okay, so we want to find what's the probability that the firm ships a defective chip. Okay? So let's name some events here. And I promise there's a probability in there somewhere. Okay? But we're going to have to work with it to get it out. The first event we should define is, let's call that event D. And that is the event that a particular chip is defective. Okay? And we know what that probability is. We'll get to that in a second. Let's define another event, event I. And event I is going to be that the inspector said the chip was defective. Okay? So note, those are two different things. The chip is defective or it's not on its own. And then there's an inspector who tries to observe the chip and determine whether it's defective or not. Okay? So those are two very different things. This exists in nature. This is some ability of a person to try to determine if this event is occurring. Okay? That's essentially how we can say that. Okay? It's a little confusing, but those are two very different things. And note, the inspector has some kind of error rate on determining whether these chips are defective or not. Okay? And so that's actually a conditional probability, which we'll see in a second. So what is it we know about the problem? We know the probability of finding a defective chip. Okay? We said that 10% of those 1,000 chips were defective. So the probability of a defective chip is 0.1. Okay? Therefore, the probability of D complement would be 0.9. Okay? 1 minus this gives us the complement of a defective chip. And note here, we're assuming that a chip is either defective or not. Okay? Defective and not defective are mutually exclusive. A chip can't be both defective and not defective at the same time. And they're collectively exhaustive. Let's assume there are only two categories, defective and not. Okay? So therefore, those two probabilities are going to sum to 1. What else do we know? We know how good the inspector is when a chip is defective and when a chip is not defective. Okay? So let's name a few of these. Okay, we were specifically given the error rate when a chip is defective. What is the error rate by the inspector when a chip is defective? So what would an error be here? If it's defective, the inspector would make an error if the inspector said it was not defective. Okay? We defined I as the inspector said that the chip was defective. So they would be making an error if it was defective and they said that it wasn't. Okay? That's the error. And that error occurs 5% of the time. Okay? Given that it's defective, what's the probability that the inspector said it was not defective? 0.05. 5% error rate. That must mean that this probability is 0.95. Okay? The complement of this, 1 minus this, gives us this. Okay? The conditioned event stays the same. We can take the complement of this event, and those two would sum to 1. Okay? So now we know how good is the inspector when the chip is defective. If the chip is defective, the inspector said it was 95% of the time. Okay? Also, we know when a chip is not defective. What does the inspector say? Okay? So given that the chip is not defective, what's the probability that the inspector said it was not defective? Okay? Given the chip was not defective, what's the probability that the inspector said that it was? Okay, this is an error. It's not defective. The inspector said that it was defective. That's an error. That happens 5% of the time. Okay? remember, there was a 5% error rate on both defective and not defective chips. Okay, so this is a 5% error rate. Therefore, the complement of this must give us this, 0.95. Okay, so now we know how good is the inspector at doing his or her job, and they're good 95% of the time. And we know, in general, what's the probability of having a defective or not defective chip in the first place. And so what we want to know is, given that the inspector said a chip was not defective, what's the probability that it really is? Okay? So our main objective as a company is to reduce the probability of shipping defective chips. We are not going to ship a chip if the inspector said it's defective. We're only going to ship out a chip if the inspector said that it's not. Okay, so the inspector says that it's not defective. What's the probability that it really is? Okay, this is the probability that we want to find, and we want to reduce that probability if we can. Okay, reducing the probability of shipping a defective chip, we're shipping it out because the inspector said it was okay. This is not the same probability as this or any of these, right? Here, this says how good the inspector is. This says, given that we've got a chip that the inspector says is okay, what's the probability that it's really defective? Okay? It's not this. It's something different. We have a completely different set of information here that we do than we do here. Okay? And how do we solve a problem like this? We can observe this. We can't observe this directly. How do we solve that kind of problem? With Bayes' theorem. Okay? Remember what Bayes' theorem was. The probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. Bayes' theorem. We can observe this, this, and this. We can't observe this directly, but we can calculate it based on what we can observe. Okay? So this is, using this kind of notation, we can calculate this down here as the probability of I complement given D times the probability of D divided by the probability of I complement. Okay? Good. So now let's put all this stuff in there. We have a lot of this already. So we have this, the probability of I complement given D, that's over here. The probability of D is up here. But we don't have this exactly, but we can calculate it based on some of our probability rules. Okay? So let's go back to this general case up here. We said this, that the probability of A is equal to the probability of A intersect B1 plus the probability of A intersect B2, where B1 and B2 are mutually exclusive and collectively exhaustive. So there's a sample space that's made up entirely of B1 and B2, and A overlaps that. So let's do this. Here's our entire sample space. Here's B1 over here. Here's B2. And here's this event A. Okay? So what is the probability of A? Well, it's the intersection of A and B1, and it's the plus the intersection of A and B2. Okay? That's the probability of A. We also said that, using some of our probability rules, that this could be written in a little bit different way. We could say that that is the probability of A given B1 times the probability of B1 plus the probability of A given B2 times the probability of B2. Okay? So this, by definition, is this thing for events that are not independent of each other. Okay? So with this idea in mind, with this thing, we can find this. Okay? Because we have conditional probabilities and marginal probabilities that would help us find this. So that's going to be the probability of I complement given D times the probability of D divided by, let's just implement this down here, the probability of I complement given D times the probability of D plus the probability of I complement given D complement times the probability of D complement. Okay? We said D and D complement were mutually exclusive, and collectively exhaustive. Okay? So this will give us I complement. This is exciting. This is exciting. I can feel it. So let's do this. Let's do the numerator. I complement given D. 0.05. Probability of D. 0.1. Divided by I complement given D. 0.05. Probability of D, 0.1. Plus the probability of I complement given D complement. That's here. That's 0.95. Times the probability of D complement. That's 0.9. So we've got this. Okay? We've got now, what's the probability that given the inspector said it was okay, that the chip is really defective? As it turns out, that probability is 0.0058. Okay? 0.0058. It's a pretty small probability. What's the probability that given that the inspector said it was okay, that it's actually defective? What's the probability that we're shipping out a defective chip? It's a pretty small probability. And why is that? Well, one, the inspectors are pretty good at their job. Not perfect, but pretty good. And the probability that we have a defective chip in the first place is pretty small. Okay? That combined together, using Bayes' theorem, gives us a pretty small probability that we're shipping out defective chips.